my name is Chris Harris, and I'm from Allery Chemistry, and welcome to this video on EDEXCEL, topic 15, transition metals. So this video is specifically dedicated to all those who are studying EDEXCEL A-level chemistry. It covers, obviously, as the title suggests, transition metals, so it's quite a large topic, but there is a large range of videos covering year 1 and year 2 available, all on Allery Chemistry YouTube channel. They're all for free, as well as some whiteboard tutorials and past paper walkthrough questions as well. So there's quite a variety of different things on there. It's all for free, and it always will be. All I ask is that you just hit the subscribe button just to show your support. And basically, as long as people keep watching and keep subscribing, then I'll keep making the videos. So there's a full range of videos on there. So go and have a look. There's loads of stuff. Also, if you would like a copy of the slides that I'm going to be showing you today, then there is a link in the description box below where you can purchase them. They're great value for money, and they're ideal for example, on your smartphone or on your tablet. You can use them there, but also you can print them off as well and use them as your revision notes. So if you just click on the link there, you'll be able to get a hold of them there. Okay, so like I say, these are dedicated to EDEXCEL, so that it's got everything that you need to know within this topic. So there's nothing in here that, if you're looking, sometimes you'll look at certain things, you think, is that relevant for me? Is that in my specification? Well, everything in here has actually been tailored to the specification, as you can see here. So it's a large topic, so it's quite a big video, but you can take bits and pieces from it as and when you require. But obviously, the whiteboard videos as well goes through all the topics if you want to look at a particular topic, but this one's dedicated to EDEXCEL. And so you can see it meets the specification in terms of, there's two main parts here, which is the principles of transition metal chemistry and also the reactions of transition metal elements. So it goes through all these different parts. So there's quite a bit of content to go through in this one. Okay, so let's start with D block elements first. So what we need to know is we need to know where the D block elements are in the periodic table, because we're going to be talking about them all the way through this video. So it's important to know where they sit. So the D block elements sit, there we are, they sit in the middle part of the periodic table, so right in the middle there, and some of these elements, are transition metals as well. So not all of them are, but some of them are. So the ones that you need to know are mainly the ones in the top row of the periodic table. So it's these ones here where you're looking at scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. So it's got all these ones right across the top here. Okay, so electron configuration. So a transition element is a D block element that can form at least one stable ion with a partially filled or incomplete D subshell. Okay, so that's vitally important. So a D subshell can hold up to 10 electrons in it, and for period 4 D block elements only 8 of these are transition elements. So scandium and zinc are not transition elements. This is because they don't form a stable ion with a partially filled D subshell. But we'll look at this a little bit more detail when we look at electron configuration, etc., because that's just as important. And so here, what we've got is the electron configurations of the 8 transition elements in period 4, and you can see that they fill up singly first, then they double up because the electrons repel each other. So it's a bit like using an analogy where if you go on a bus and you've got everybody, so imagine you've got a bus and everybody's occupying singly a seat. And there's a couple of seats which are spare, so nobody's sitting there. So what you would normally do, well, what I notice anyway, I don't know about you, but what I notice is that normally people go and sit in the empty seat because they don't want to sit next to anybody, but they'll only sit next to somebody if there's no other seats available. Now electrons have a similar principle where they will fill up an orbital singly first. If there's a spare orbital, it'll go in there, and it isn't until all the orbitals are full that they have to then pair up because there's nowhere else for them to sit. So this is quite important. So if we look here, we're going to look at a transition metals. Now what we're going to do is, you'll see I'll put the electron configuration near the side. Well, the electron configuration will pop up here, but I'm only showing the last the last electrons, so the valent electrons. And so the electrons before that, obviously there are electrons before that. What we could do is we can use a square bracket with a noble gas element in there. So this is argon. So basically all of these here, what you're going to see, have the electron configuration of argon plus whatever you see on the screen. Okay, there we are. Okay, so that's the electron configuration for argon. Right, okay, so if we look at titanium first. So titanium has 2 electrons in the d orbital and 2 in the s orbital. And then if we go across, we go to vanadium. The 3rd electron then sits in the d orbital, which is fine. And then again, chromium also sits in there. But you'll notice something a bit odd happens at chromium, because one of the electrons in the 4s orbital, which is here, one of these electrons actually jumps into this orbital here. Okay, so the reason why it does this is because it has an opportunity where it has a full, half-full subshell. Okay, this is quite stable. This is a stable setup configuration. But then what happens for the next element, which is manganese, is the extra electron actually goes back into the 4s orbital because that is lower in energy, so it sits in there. So this is where it pairs up at this point. For iron, the next electron goes into the first orbital, as you can see here. The next one obviously fills in the second one, which is cobalt, and then nickel, obviously that sits in there. Now, again, we've got another funny setup here with copper, where the electron again from the 4s orbital jumps back into the 3d orbital, and that forms a full d subshell. That is more stable than having the electron sat in the 4s orbital. Okay, so that's quite important. Now, the next element after that is zinc, and zinc has the electron goes into the 4s orbital for zinc. So chromium and copper, like I said, they behave differently. An electron from the 4s orbital moves into the 3d orbital to create a more stable half-full or full 3d subshell, respectively. So very, very important. You need to know the electron configurations, and they may ask you for the configurations of chromium and copper in particular because of their unusual setup when writing electron configuration. So as long as you're aware of that, that's the main thing. Okay, so let's look at scandium and zinc, because these are a little bit strange as well. So scandium and zinc are not transition elements. That's very, very important. Scandium only forms one stable ion, which is scandium 3+, and it has an empty d subshell when that ion is formed. So because it's not partially filled, it's not classed as a transition element. It's a d block element, but it's not a transition element. So you can see here, this is the electron configuration of scandium as an element, but clearly, obviously, when we take the 3 electrons away, you can see it doesn't have any electrons left in the shell. There it is there. Okay, so it has none left. So because it's not partially filled, it's not a transition element. And if we do the same for zinc as well, zinc only forms one stable ion, which is zinc 2+, and zinc 2+ has a full d subshell. And so therefore, because it's not partially filled, it's not a transition element. I must emphasize, it's the ion that we're looking at, not the actual element here. Okay, because you might look at that, particularly scandium, and say, well, hang on, scandium's got a partially filled d subshell. It's the ions that make it that we're looking at here. Okay, so you can see here, zinc has a full 3d subshell and a full 4s subshell. So when we take the 2 electrons away, and you'll see this later as well, actually we take them from the 4s orbital first, and obviously this still leaves a full 3d subshell for zinc 2+. So that means it is not a transition element because it doesn't form a partially filled d subshell. Okay. Okay, so let's look at the electron configuration of some of these. So transition metals lose electrons in a specific way to form ions. Okay, so let's look at the electron configuration for Fe3+. So what it does is it loses 3 electrons, 2 from the 4s, and 1 from the 3d. So we always lose from the 4s orbital first. And you can see we've got our configuration to the right there, the top right. So there's our configuration for iron as normal. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. So all of them are listed on there, and you can see the electron configuration. But what happens when we take the 3 electrons away to form Fe3+, we get this electron configuration. And you can see what we should do is add up all the numbers on the smaller numbers on the top, iron has 26 electrons. We've taken 3 away, so we should have 23. So always check your electrical configuration to make sure the smaller numbers must add up to give the number that you require. So you can see here we lose from the 4s first. There it is. And then the 3D. So we have this configuration here. So Fe3 plus, as you can see, does have a partially filled 3D subshell, as you can see here. So therefore it is a transition element. Okay, so transition metals have specific properties, and really the whole chunk of this is going to be looking at the properties of them. So by looking at variable oxidation states, looking at coloured ions in solutions, and they're also good catalysts. And the basis, the fundamentals, I suppose, of this video is looking at all of these properties here and also their reactions as well. So we'll look at the variable oxidation state, the coloured ions in solution, the colours. There's a lot of colours in transition metal chemistry that you need to know as well, and obviously catalysis as well. They also form complexes, but we'll look at the complexes as well soon. So transition metals have variable oxidation states because the electrons sit in the 4s and 3d orbitals, and these energy levels are actually quite close, and we've seen that in the previous slide where we looked at the electrical configuration of some of the transition metals. So as a result, the electrons are gained and lost using a similar amount of energy, so there's not really a massive difference there. And so when they form ions, obviously we're losing electrons, we're forming ions, they actually have various different colours. And we'll look at the colours in a moment. There's a big table here with all the colours around it, but this table here is just showing you the ions that they form. And you can see here that we have various different ions for things like vanadium, chromium, manganese, iron, for example. And it goes all the way across, and you can see all our different elements here. So remember, scandium though is not a transition element, so it forms Sc3+, but remember it doesn't have a partially filled D subshell. So it's all the rest which are actually coloured, and they form these nice bright colours when they form complexes, and we'll look at complexes later. So, like I say, they also formed coloured ions in solution as well. So, and the next slide shows the colours of these when they're dissolved in water. So let's have a look. Okay, so we brought that table back. Now, you need to know the colours of these. Okay, these are the ions when they're dissolved in water. So we put all these into water. The ones that you don't need to know are the colours of titanium, manganese, or nickel. So you don't need to know any of them, but all the rest you do. So let's have a look. So violet. V2 plus is a violet colour, V3 plus is green, VO2 plus is blue, and VO2 plus is yellow. And then chromium 3 plus is a bit of a strange one. It's green and violet, but it's violet when it's surrounded by 6 water ligands, and we'll look at ligands later. And they're normally substituted, so it looks green. So it can have it's normally green colour when we look at it, but it can exist as violet if it's in the right conditions. Okay, orange for your dichromate. Manganese Mn2 is a pale pink colour. MnO42- is green, and MnO4- is purple. It's a nice purpley colour. Okay, so it's your manganate. Iron 2 is a pale green colour. Iron 3 is yellow. Copper 2 plus, or cobalt 2 plus, sorry, is pink. It's definitely not copper. Nickel 2 plus, as I say, you don't need to know the nickel ones or the manganese ones, but it's just there for your reference. But it's green. Copper is a pale blue colour, and obviously you've got your titanium ones such as purple and violet, but you don't need to remember them colours. So it's just the ones that you can see there, all of them on there, apart from titanium, manganese, or nickel. You don't need to remember the colours of, so it's not the full amount, but it just gives you an idea. You can see the variety of colours that these transition metals provide. It's a really nice area of chemistry. It's probably one of my favourite areas of chemistry. Looking at forming all these different coloured compounds that's used in pigments and paints and dyes, and so there's loads of different examples here. Okay, so metal complexes. So another property of a transition metal is their ability to form complex ions. So we've seen that they can form coloured compounds. Catalysis will come later, but they can also form these complex ions as well. So a complex ion is where a central transition metal ion is surrounded by ligands and is bonded by dative covalent bonds or coordinate bonds. So you'll remember that from the bonding topic in year 1 chemistry. So if you're not familiar with that, go and have a look there. Basically, we have this structure here on the right. So we have a central metal ion in the middle there, as you can see. We have ligands that surround it. So ligands have at least one lone pair of electrons, and these are used to form a dative covalent or coordinate bond with the metal ion in the middle. We have square brackets as well, and the square brackets show the full complex, and the overall charge of the complex sits outside of it, as you can see there in the top right. So the complex ions can come in different shapes as well, and we'll have a look at them later. Okay. So let's look at a ligand, because obviously we've seen a ligand surrounding the metal ion there. Now a ligand can either be an atom, an ion, or a molecule, and it must have, remember what we just said there, it must have one lone pair of electrons. And it can either come in monodentate, bidentate, or polydentate ligands. Okay. So ligands which only have one lone pair of electrons are classed as monodentate, or also known as unidentate ligands. So these include things like water, for example, because there's a lone pair in the oxygen. Ammonia has a lone pair in the nitrogen. Chloride ion, and obviously the OH minus, the hydroxy group, which has the lone pair on the oxygen as well. So these are the ligands, the monodentate ligands that you need to know about. Ligands which have two pairs of electrons are called bidentate ligands, and you need to know these specific examples. So one is ethane diuate, which is basically a dicarboxylic acid with the hydrogens obviously removed, so they have the lone pair of electron on the oxygen. And also ethane 1,2-diamine, which is obviously your diamine that's presented there. You do need to know both of them, and you will see them within your complexes as well. So ligands which have more than one coordinate bond are called multidentate ligand. No surprise, multi meaning just more than one. And so a classic example is EDTA 4-, and you'll also see heme as well later on for hemoglobin. But EDTA 4- is an example of a multidentate ligand. It can bond 6 times, so it's quite a monstrous ligand, and it forms 6 coordinate bonds with the central metal ion in the middle. Okay, so remember we said that you can get complexes that come in different shapes. So we're going to look at the shapes here. Now the shape is dependent on the size of the ligands and the coordination number as well in our complex. So the coordination number, I must emphasize this because sometimes people write down the wrong thing or they get this a little bit confused. But the coordination number is the number of coordinate bonds in the complex. It's not the number of ligands, okay? So for example, EDTA can form 6 coordinate bonds, but there's only one ligand. So the coordination number for a complex with EDTA is 6. It's not the number of ligands, so it's not 1, okay? Very, very important that. And so some of the ligands are quite small, and you can actually fit 6 of these around a central metal ion. So for example, you've got water, you've got ammonia, and you've got hydroxide ions. So you can imagine these, and I use an analogy of pigs round a trough. So imagine you've got a trough full of food, and the trough is a fixed size, so that's a bit like your central metal ion, okay? You have loads of pigs, and the pigs are ligands. Now, if the pigs are small, you could fit more of them around that trough, and they can squeeze in. If the pigs are bigger or fatter pigs, then you can't fit as many of them around, and you're limited because the ligands are a little bit bigger. So this is exactly the same, except this is to do with the size of the ligand around the transition metal ion. So some ligands, like we say, are larger. Chloride ions are larger, Cl-. Your water, ammonia, and hydroxide are smaller ones. Now, ethane diuate and ethane 1,2-diamine are larger still, and normally we can only fit 3 of these around a central metal ion. So the size of the ligand does have a strong influence on the coordination number, and obviously how that's structured, the shape of it as well. So complexes with a coordination number of 6, they form octahedral shapes. So here's an example here. So we've got water surrounding a cobalt metal ion in the middle there. So it's also written as COH2O6 with your 2+ on the top there. So it's got 2+ charge. And here's another one where you've got ammonia ligands surrounding the cobalt in the middle there. Again, that's classed as a small one, so it can also be written as that. So notice the square bracket when we're writing them like this. So the square bracket basically tells us what ligands are surrounding the metal ion in the middle. So you'll see that quite often, actually, a lot of equations written like that in future. So all these bonds are octahedral. So you remember from doing shapes of molecules in year 1 chemistry that octahedral shapes always have a 90-degree angle between the bonds. Okay. So complexes with a coordination number of 4, they form tetrahedral and square planar shapes. So let's have a look at this one. So this is chlorine. Remember, the chloride ligands are bigger, so you can't fit as many of them around that central metal ion. So this is copper, with 4 chlorine ligands around it. Also written as that, so CuCl4, 2-. Okay. Bond angles in a tetrahedral complex are 109.5 degrees, so you'll remember that again from year 1 chemistry. But you also need to know this one as a specific example of a square planar. So don't worry too much about, how do I know if it's tetrahedral or square planar? You just need to know that this one here, this complex, is, this one's called Cisplatin, but that this one is a square planar complex. So it's also written as this, okay? So you've got your 2 ammonia ligands and 2 chloride ligands surrounding it. So this is a specific example of a square planar, and this is the one that you need to know. All the other ones are tetrahedral, apart from this one, and you do need to know this one. Unless, of course, they give you something different in the exam and tell you it's square planar, then it's obviously drawn like this. So this one's called Cisplatin. It's an anti-cancer drug. And the bond angles in a square planar complex are always 90 degrees. Okay, so again, that's from year 1 chemistry. Okay, so complexes have an overall charge which is the same as its total oxidation state. Okay, so that's the oxidation state of the transition metal ion in the middle, whatever its oxidation state is, and depending on what ligands are surrounding it will depend on the charge that you have, overall charge on that complex. So the formula is very simple. Total oxidation state of the metal equals total oxidation state of the complex minus the total oxidation state of the ligands that are surrounding that metal ion. So let's have a look. Let's bring this example back up again with our 4 chlorines surrounding our copper ion in the middle there. So the overall charge, remember, on the outside is -2. That's the overall charge of our complex. Each chloride ligand, or Cl minus, is a -1. And we have 4 of them, so that's a total of -4 in total. So the total complex oxidation state is -2 in this case. So the oxidation state of Cu, which is copper, is -2 minus -4 equals +2. So you've got your oxidation state is -2, that's the overall one. Total oxidation state of the ligand, so it's minus, obviously, is -4. So the oxidation state of copper in the middle is +2. Pretty straightforward, I think. Okay, so remember when I said about EDTA, and I said it was a polydentate ligand, or multidentate ligand. So you've got a lot of different sites which can bond to that central metal ion in there, and EDTA was one of them. Another one is hemoglobin. So heme is a multidentate ligand, and it's found in the molecule hemoglobin. So for all you biologists out there, so anybody who's also studying biology, this will be fairly familiar with you. So obviously you may not need to know it in as much detail for chemistry, but we need to know some of the chemical aspects of hemoglobin, because it is quite an important complex. So hemoglobin is actually a protein, and it's used to transport oxygen around the body. Okay, so we've got our iron in the middle, as you can see there, and we've got globin protein here, and obviously our ligands at the top here. So you've got water and oxygen. I'll come on to that in a moment. The structure is octahedral, so you can see the structure there. So it's got 6 coordinate bonds around it. And 4 of the nitrogens, you can see, is shown by the circle, just to show that's all part of one molecule. Comes from the multidentate ligand called heme. Okay, so that's your ligand, is heme. So one of the coordinate bonds comes from a large protein called globin, hence hemoglobin. And then the final coordinate bond comes from either an oxygen or a water molecule. And now this is going to be quite important because actually the oxygen and water molecule plays quite an important part in how hemoglobin works to transport oxygen in particular around the body. Okay, so like we say, it is a transporter of oxygen. So we're going to see how this works. So simply, oxygen substitutes the water ligand in the lungs where oxygen concentration is high, because obviously that's where we breathe in air, which contains oxygen. There's loads of oxygen in there. So what happens is the oxygen ligand, oxygen binds as a ligand to the top of the hemoglobin on top of the hemoglobin molecule with the coordination bond obviously at the top there. So this is transported around the body and taken to, for example, muscles to allow respiration to occur. So oxyhemoglobin gives up the oxygen to a place where it's needed, such as your muscles, and water takes the place, and hemoglobin returns back to the lungs and start the process again. So actually, that water ligand that now sits on the top is only attached once the oxygen has been deposited in the place where it's required. Now, this kind of makes sense to an extent, because actually when we breathe out, like that, okay, although you didn't need that example, but when we breathe out, we actually breathe out water vapor as well, and that water vapor has come from, is a product of respiration in our cells, and so that water was sitting on our hemoglobin molecule there, and is obviously released out through the lungs, and then once it releases the water, it'll pick up an oxygen and then go back to the muscles again, so it'll constantly do that, so it's quite busy, as you can imagine. Now, there is a downside because obviously what's transporting this around the body is all to do with the bond between oxygen and water and the central metal ion in our red blood cells. But also we can have some dangerous chemicals such as carbon monoxide, which I'm sure you'll be fully aware is toxic to humans. And this is how it works. It causes headaches, unconsciousness, and even death. And they call it the silent killer. You can't see it, you can't smell it. And quite often, if there is carbon monoxide in the room, and if you're asleep, for example, and there's carbon monoxide in there, you just don't wake up. There's no alert there. You just become unconscious, and it's a lethal gas, and that's why generally carbon monoxide is produced through incomplete combustion of a fossil fuel. So it comes from boilers. So if you've got a boiler in the bedroom, then it is good practice to have a carbon monoxide alarm near it. So if there is carbon monoxide present, it will detect it, sound the alarm, and then you can wake up and get out of the room. So, but most boilers are fitted in garages for that reason, to keep them out of the way. So if they are not burning properly, then if nobody's living in there, it doesn't really matter. So it is important. So carbon monoxide, CO, is inhaled, and the water ligand is actually replaced with a carbon monoxide ligand. So you can see the diagrams here. We have water ligand on the left there. You can see it there. There's your water ligand. So that's normally in the lungs. But instead of picking up oxygen, it picks up carbon monoxide, and that bonds onto the ligand there. Now I think you can probably see what's going to happen now. So obviously carbon monoxide bonds strongly, much more strongly than oxygen, and it readily replaces either of them ligands. So that's not a good sign because it bonds too strongly. And so that means there is less. The hemoglobin that's going around the body is actually carrying carbon monoxide. It's not carrying oxygen molecules. And because there's no oxygen molecules there, the oxygen levels in the blood drop, and that's what makes you dizzy, and that's what makes you go unconscious, because there isn't enough oxygen going to the brain to keep you awake. Okay, so this is why carbon monoxide is poisonous. It's all to do with the strength of that bond to an ion. Who would have thought it? So yeah, so you need to be able to know that within for EDEXCEL chemistry. Okay, so we're going to look at something called optical isomerism. Okay, because you have optical isomerism within complexes, and we're going to look at some examples there. But what we need to know is this type of isomerism in particular. Now, you've seen isomers already in year 1 chemistry, so this is just another type of isomer, but it has to meet a certain criteria, and we're going to look at that here. So complex ions, they show optical isomerism, which is a type of stereoisomerism. So complexes are optical isomers when they're non-superimposable mirror images of each other. So you can see here, we've got two complexes here, two ion complexes. And what it has is we've got our diamine molecule here, so ethane 1,2-diamine, which is here, and this is bonded to our iron. Notice we can only fit 3 of these because they're quite big, and you can kind of see it quite nicely there. But these complexes here are actually mirror images of each other, so they're non-superimposable, so they can't be superimposed over each other. And we have a mirror line down here showing the non-superimposable mirror images. So octahedral complexes with 3 bidentate ligands show optical isomers, and like we've seen on the left there. So we need to be aware that there is optical isomerism in transition metals, and it is a type of isomerism that's quite important actually, because it allows us to maybe for drugs in particular, allows us to tweak a drug to target particular parts of the cell, etc. Okay, complex ions also show cis-trans isomerism, which is another type of stereoisomerism, and it's a branch of EZ isomerism. So octahedral complexes with 4 ligands of the same type and 2 ligands of a different type, these do display cis-trans isomerism. We can see it, the complex here, we've got 2 ligands which are the same, these are your chlorine ligands here, and 4 which are different, and again we can see it here, but you can see the chlorine positions have changed. So this is a type of cis-trans isomerism. So there you go. So if the 2 different ligands are opposite each other, so if you see on the left we have something called the trans isomer because they're opposite, so you can see there, and obviously if they're next to each other we call that a cis isomer because they're adjacent to each other, they're sitting next to each other. So that's fairly straightforward, there's nothing too difficult there. Okay, so square planar complex ions also show cis-trans isomerism. So we can see here that we've seen this one before. This is one of the specific examples that you need to know for a square planar complex. So square planar complexes with 2 ligands of the same type and 2 ligands of a different type, these display cis-trans isomerism. So you can see here this is our anti-cancer drug. So this one is trans, which is on the left there. So you can see the reason why this is trans is because our ammonia and chlorine ligands are opposite each other of the platinum. So this is a trans complex. And obviously if they're on the same side, then this is cis. So this is on the same side. So you can remember that as like transatlantic, for example. So opposite the Atlantic. So trans means opposite. Okay. So let's look at d-orbital splitting. So d-orbital splitting is really looking at the reasons why these transition metals are so colourful is mainly down to this phenomenon here. So there's a little bit of physics creeping back in here as well. So the D subshell is split into 2 when ligands bond with the central metal ion. So we've got the central metal ion, the ligands bond to it, and what happens is the D subshell, instead of having a nice neat 5 orbitals in a row, that actually splits into 2 different parts. So you can see here, here's our 5 orbitals in a row. So this is the 3D electron configuration for cobalt 2 plus ion, but there's no ligands attached to it, let's assume, okay, in this example here. So in this example, when we attach ligands to it, something weird happens, and these 5 orbitals start to split into 2 different levels. So you've got a distinct energy gap that's created between these 2, and we call an energy gap delta E, so it means change in energy. Okay, so the delta means change in. So this is what we call a ground state, and we're going to have a look at a different state in a moment. But effectively you've got 3 orbitals here at the bottom and 2 at the top here. So this only happens when we take a transition metal ion and ligands are bonded to it, so it has this weird effect. So when electrons absorb light energy, so this is obviously from the surroundings, some of these electrons move from the lowest energy level, the ground state, to higher energy level orbitals, which is called an excited state. Okay, so it's very, it's like football, isn't it? It's like promotions and relegations, so it's about trying to move these electrons. If we give enough energy, some of these electrons will jump up to that higher energy. So here's an example here. Here's an example of an excited state ion. So you can see, count the number of electrons in the bottom here. You've got 2, 4, 5 electrons at the bottom, 2 on the top. We give it a little bit of energy, and what happens is one of the electrons in here now jumps up into the orbital above. So this is an excited state the ion is in. So remember, and if you've seen some of the videos, I always say that atoms and ions and molecules are incredibly lazy. They don't want to be in a state where they have too much energy. And now what we've done here is we've taken one of the electrons and forced it into that higher energy. That just isn't good. So to do that, we have to put energy in, and that can be visible light, it could be UV, it could be infrared, it could be any type of energy. The energy that we put in must equal the energy of the gap here. It depends, that is dependent upon that. But what happens, so this is what I'm saying. So in order for this to happen, the energy from the light must equal your delta energy, that energy gap there. So the size of that delta E, the size of that gap, is dependent on a few things, okay? So the central metal ion and its oxidation state, so that's dependent on it. The type of ligand that's bonded to it, so it could be a water, an ammonia, a chlorine, for example, that has an impact. And the coordination number, so that's effectively the shape of the complex. Is it octahedral, tetrahedral, square planar, etc.? So, loads of factors here which can alter or change that energy gap, and that energy gap is depends on the color, which we're going to look at. Okay, so color, remember, is one of the traits of a transition metal, and this, like I say, this is the physicsy bit. So this is where we're going to look at why they're colored, and we're going to look at energy, and we're going to look at frequency and things like this. So some frequencies of visible light are absorbed by transition metal complexes, and the frequencies absorbed depend on the size of delta E, which is that gap between the split d orbital. So you can see here, as we go from, if we take the colours in the visible light spectrum, we start with red, which has the lowest frequency, which is at this end of the spectrum, and purple, violet colour, should we say, at the top here, has a higher frequency. And so the larger the energy gap, that delta E, the higher the frequency of light is absorbed. So we need a higher frequency to do that, okay? So that's the energy that's required to take an electron from a ground state to an excited state. How exciting is this? Okay, so any frequencies which are not absorbed or reflected, any frequencies which are not absorbed are actually reflected or transmitted. So if the ones which, for example, if we have a transition metal ion that absorbs at green, let's say this frequency of light, then all of the other colours around it are reflected or transmitted. So the ones which are not absorbed, these are reflected or transmitted back out of the complex. So the combination of all these frequencies, of all these different colours, the ones which aren't absorbed, they actually create a complementary colour that we actually observe. So this is what we actually see. And we can see here a colour wheel, and it shows the complementary colours here. So for example, your cobalt hexa aqua complex here absorbs frequencies that produce red light. So it absorbs the red colour here. So it's at this spectrum here. So the complementary colour is light blue, which is the cyan colour here. So this is the colour that we observe. That colour has come about by combining all the other frequencies that weren't absorbed, and that gives us this colour here. Okay, so that's what we observe. So we observe the reflected or transmitted radiation that wasn't absorbed by the complex. That's fascinating. Okay, so for these complexes where we have a full or empty 3D subshell, no electrons can migrate to higher energy levels. So this means we see these complexes as colourless or white. So these are complexes with a full D subshell, or where they have no electrons. So we can get colourless or white transition metals as well. So that's quite important. Now you'll look at things like, things where a classic example is zinc. Zinc doesn't have any space where it can migrate these electrons, and that's why zinc compounds are generally white or colourless. They don't have any colour because they can't actually move electrons up and down. Look at scandium, for example. It doesn't have any electrons at all. In scandium 3+ doesn't have any electrons at all, so we can't move anything that doesn't exist. So that's why they don't form coloured ions. So you can see why transition metals fit that criteria. You must have a little bit of capacity up and down. It's a bit like double-decker bus. You've got space upstairs, space downstairs. Okay, so that's quite important. Okay. So the colours, like I say, the colours that we see are complements of the colours that are absorbed by the solution. So remember, white light is made up of the colours that we see above, so it's that spectrum. And you might remember the acronym Richard of York gave battle in vain. So that acronym helps to remember the colours and the order of the colours. But when this hits a transition metal solution, only one of the frequencies out of all that white light that we see is actually absorbed. And any frequencies which are not, like I say, are reflected or transmitted. And the combination of these creates a complementary colour that we observe. So essentially, if we mix the complementary colour and the absorbed colour by the complex, we get our white light back again. So that's effectively the idea behind it. So like I say, the colour wheel allows us to predict the colour of the light that was absorbed. And the colour directly opposite is what is absorbed here. So you are expected to be able to spot this. So for example, a green colour absorbed would mean that a green colour observed, would mean a magenta colour has been absorbed. So we can actually use this colour wheel to work out what frequency or what colour has actually been absorbed. So we can work it backwards. Okay. So remember what it's actually based on as well. So what actually can affect that. Okay. So redox potentials tell us how easily an ion is reduced, which is the same as the electrode potentials. Okay, so this is where we're looking at electrode potentials, which you will have seen in the previous topic to do with Redox 2. So that's that topic there. Redox 2 goes into basically cell potentials, so forming electrode half cells and full electrode potential cells. So if you're not too sure on that, then you're going to have to look back at that video there in the year 2 playlist. So this one's going to basically, them potentials that we're looking at tells us how easily an ion is reduced, which is the same as the electrode potential. So let's have a look and link this together. So the least stable ions have the largest redox potential, okay, and are more likely to be reduced. So let's have a look here. So we've got zinc 2+, plus 2 electrons will form zinc, and we give that an electrode potential of minus 0.76. Copper 2+ and 2 electrons to copper has an electrode potential of plus 0.34. Now we can see here that the copper one here has an electrode potential of 0.34, and so what this means is it's less stable than the zinc 2+, which has a lower E0 value. Okay, so your copper one is less stable. So remember that E0 values, okay, have to follow the following standard conditions. That little underground symbol that you see on there, this one here, okay, this symbol here, this says that it must be under standard conditions. And the standard conditions are 298 Kelvin, 100 kilopascals, and solutions at 1 moles per dm cubed. So just remember that, that's quite important. So there may be a difference in redox potential to the standard values seen in a data book. And it is dependent on the environment that the ions are in. Okay, so you can look, remember electrode potentials, you don't need to remember them, you will be given that data. But electrode potentials are obviously listed in a book or in a table, and there's loads and loads of them. But that is only true if it meets these standard conditions. If it doesn't, then the values are going to be different. Okay, so let's have a look, and we're going to show you some of the electrode potentials as well within these areas of chemistry, so you'll see the values pop up here. So we're going to look at the first type of chemistry, and I love vanadium chemistry. It's got so many different colours attached to it, but the first one is vanadium chemistry. So vanadium is a transition metal that has a wide range of different oxidation states and colours. It's really nice. So when transition metals change oxidation state, a redox reaction occurs. Okay, so when they're going from one oxidation state to another. So let's have a look. So half equations show the reduction of ions and atoms with the reduction potential, or E0, and they are listed below. So let's have a look. So here we've got ions, we've got an oxidation state, we've got a reduction half equation, the reduction potential, which is E0, and the colour. So let's have a look. So vanadium 2+ has an oxidation state of +2. And so when we're transitioning between vanadium and vanadium 2+, then we have a reduction potential here. So this is going from V2+ to V to minus 1.18 volts. And this is a violet colour. We get this nice vibrant colour there. So the next one is V3+. So V3+ has an oxidation state of +3. So you need to know these. V3+ going to V2+. You don't need to know these figures, obviously, but you do need to know the oxidation state and the colours associated. So V3+ going to V2+ is minus 0.26 volts. And this is a green colour. VO2+ has a +4 oxidation state. That's the vanadium. And the reduction half equation here is VO2 plus 2H plus an electron forms V3+. This is going back here and to H2O. So you can see how all these link in. So the products here are the reactants in the previous step. Okay, and then that gives a reduction potential of plus 0.34 volts. So that is a blue colour. See how colourful these are. And VO2 plus, don't get that confused with the other one, has a +5 oxidation state. We've obviously got a half equation there as well, and a reduction potential of +1 volt, and this is yellow. So the bits you need to remember are obviously the oxidation states, the types of ions, and the colours of them. Obviously everything else, the half equations and redox potential values, will be given to you because you're not expected to remember them. So the reduction potentials that we've just seen there, these can be used to work out if a reaction involving transition metals is likely to happen. So remember, you can have a look back at topic 14 for that, which is on, it's called Redox 2. And so that has a lot of information about predicting reactions. So remember, though, a redox reaction is only feasible if the E0 value is positive. Okay, so the electrode potential. So using the information stated in that previous slide, so we had all that information there, we can observe the colour changes possible when we add zinc metal to VO2+. So that was the last one in that table, in acidic solution. And we've got the zinc half cell here, which is zinc 2 plus 2 electrons gives zinc, and that's the electrode potential there. It's negative. So like I say, you'd be given the vanadium half cells. You don't need to remember them whatsoever. So first of all, the VO2+ is reduced to VO2+. Okay, so like I said, don't get them confused. Make sure you're really clear with that. And there's a colour change of yellow to blue as we'd seen previously. So here it is here. So we've got our electrode potential of plus 1.76, okay, for this reaction here. So we're going from VO2 plus zinc, 4H plus will form 2 VO2 plus, zinc 2 plus, and H2O. So these equations here were taken from the previous slide. And we go from our yellow colour here, and it goes blue to VO2 plus. So effectively, we've reduced our vanadium, okay? So then the vanadium VO2 plus here, so vanadium oxide instead of vanadium dioxide, is reduced to V3 plus, and there is a colour change of blue to green. Okay, so the electrode potential is plus 1.1 volts. So that's the overall equation there, and it goes to V3 plus. Okay, so remember, they're only feasible if E0 is positive, which is fine. So these are positive, so they're feasible reactions. Okay, and so the final step is the V3 plus is reduced to V2 plus, and the colour change goes from green to violet. So there's the reaction, and it goes to V2 plus. Again, E0 value, you can see there, is still positive, so it's still a feasible reaction to do. Okay, so you need to be aware of these colour changes in the transitions, and obviously given the half equations from your redox potential tables, you are expected to construct the full equations like you see here, and be able to calculate obviously the E0 value of them given the figures. So remember the total E0 value is the E0 of the reduction process minus the E0 of the oxidation process. Okay, so this V2 plus, okay, going to V is the last one here. So this is forming vanadium, is minus 0.52. So you can see, under standard conditions, this reaction will not occur because our E0 value is negative. So it's really difficult to, under standard conditions, to go from V2 plus to get your vanadium solid that's produced. Okay, so let's have a look at chromium chemistry now. So chromium chemistry is, again, quite vibrant. It's a nice, you see lots of different colours with this one as well, just like with vanadium. Variable oxidation state, and they mainly occur in +2, +3, and +6. And you need to know the reactions of these as well, because it's a specific area of chemistry. So again, we're going to look at the ion in solution, so what that is, its oxidation state, and the colour when it's in solutions. This is dissolved in water, and we've got some additional notes as well to look at it. So the first one is dichromate, so Cr2O7 2-. Chromium has an oxidation state of +6 in this compound. It's a nice orange colour, okay, if you've seen this before. It's also known as, like I say, dichromate 6 ions, and they're really good oxidizing agents. So you might have seen it used in titrations, for example, as an oxidizing agent. The next one is Cr04 2-. It has a +6 oxidation state. It is yellow. It's a nice yellow color, and it's also known as chromate 6 ions. And so these are also good oxidizing agents. So the same oxidation state, but a different color. Okay, so it's Cr04 2- instead. The next one is chromium 3+. So chromium 3+ has obviously got a +3 charge. It is green. Okay, so it's a green compound is formed. This is the most stable ion when it's surrounded by 6 water ligands. Remember seeing the complexes before. But when it's surrounded by these 6 water ligands, then we get a violet solution is formed. So remember that with that funny one at the end. So, but you have Cl- impurities to replace the water ligands, and it makes it look green. So in theory, it is violet, but we observe it as green because of the chloride impurities that you find in water as well. And the last one is Cr2+. This is +2 and is a blue color. Okay, so we're getting loads of different colors here, as you can see. Okay. So chromium ions, they can undergo reduction and oxidation as well, as they have many different oxidation states. So that's one of the key factors of a transition metal. And here we're going to look at how chromium ions can be reduced. So here we've put the E0 values on here just for reference, but this is a feasible reaction, as you can see, because it's a positive E0 value. But you can see here we've got dichromate here, which is this one. And we're using zinc, and you might have seen this reaction. You literally just put chunks of zinc into your dichromate solution. It's got to be acidified as well, so it's just dissolved in an acid. And then we've got we form your Cr3+ here because we've reduced it, zinc 2+, and water. And here, obviously, you've got your dichromate ions are being reduced. Zinc is the catalyst here. So you can see here we've gone from a +6 oxidation state for chromium to +3, and we get a color change. It goes from orange to green. So that is an indication of chromium being reduced, and hence the zinc is being oxidized because it's gone from 0 to +2, which is there. Okay. So zinc can be used to reduce Cr3+ ions further to Cr2+, so you can keep on going. However, Cr2+ is really unstable and readily oxidizes back to your Cr3+. It's really difficult to form Cr2+. I'd be very surprised if you've managed to hold on to it in the lab, but it can be done if it's done in an inert atmosphere. The E0 value is +0.35, so it's still feasible, just about. And here's the overall reaction. So Cr3+ going to Cr2+. Obviously, your zinc. So here we go. So it's gone from +3 to +2. So we're going from green to blue, and our zinc is gone from 0 to +2. So the zinc is being oxidized because the oxidation number is increasing, and your chromium is being reduced because it's gone from +3 to +2. So that's decreasing. Okay. So here we can look at how chromium ions can be oxidized. So we're just going backwards here. So we can see here we're starting from Cr3+, and we're going to form our Cr04 2-, and you can see here that you've got an E0 value of +1.08, which tells us that this is a feasible reaction. So they are oxidized using hydrogen peroxide in an alkaline solution, and what we form is a yellow chromate substance is produced. So you can see here we're going from +3 to +6, so that's definitely oxidation because the oxidation number is increasing, and we're going from a green to a yellow solution, so that proves that this reaction is actually working. And your chromate ions, this is very important because these have both got the same oxidation number of +6, remember? So chromate 6 ions, Cr042-, exist in equilibrium with dichromate 6 ions, which is Cr2O42-. So there's an equilibrium between the two. So if we add acid to the yellow chromate ion solution, this creates the orange dichromate solution. And this exists in equilibrium, so it is a reversible reaction. So this should be a this should be a reversible reaction because it goes forwards and backwards. So here it is. Here your chromate 6 ions reacting with your acid to effectively form your dichromate and water, which is on the top there. So your oxidation states, they haven't changed. So this is not oxidation. Okay. If we go back, so this is not oxidation. This is just a reaction that exists in equilibrium. They exist in tandem with each other. Okay, so let's look at some amphoteric chromium hydroxides. So remember, amphoteric means it's something that acts as an acid or a base. So you would have seen that in the acid-base equilibrium topic as well. So if you're not sure on that, go and have a look there. This means that obviously they're amphoteric, and we can hydrolyze metal aqua ions to form insoluble chromium hydroxides by adding a base. So we can either add hydroxide ions, which are OH-, so like sodium hydroxide, or we can add ammonia to it. Either one will work. So let's have a look at their reactions here, what we're doing. So we've got our hexa-aqua complex here. So this is basically just chromium added to water. So it's chromium solution. We've got this nice green colour. And if we add a hydroxide to it, say a sodium hydroxide, so this is a small amount of hydroxide, then what we get is this complex here. Now, if you notice, and we'll look at this in a little bit more detail as well, but we've got 6 ligands in total. 3 of them are water ligands, 3 of them are hydroxide ligands, and they form a solid complex. The reason why they form a solid complex is this now has no charge. Remember, this complex here had a charge, a 3+, but we've added 3 negative ligands, and that balances out the 3+, and it forms a neutral solid complex, and that's why we see a precipitate. Same again with ammonia, exactly the same, will form a solid precipitate. The ammonia takes one of the protons from 3 of the water ligands, and it forms ammonium ions, which are down here. So it's 3NH4+, that's where that comes from. And we get this greeny-grey precipitate when we conduct this reaction. So chromium hydroxide, so CrH2O3, is amphoteric. Okay, so when we add a base to it, it acts as an acid and donates H+ ions to react with the OH- and it dissolves. So you can see here, there it is. So we've got add a small amount, or add hydroxide ions to this, so it's an excess. Now actually what we form is chromium hydroxide. It becomes, you get a negative charge in it now because we've added 3 more OH- ions to it, and it dissolves. Okay, so because it's got a charge again, it's a negative charge. And likewise, when we add an acid, it acts as a base by accepting H+ ions, and it also dissolves again. So here it is here. So we add our acid and we form chromium H2O6. So the 3 hydroxide groups that were on this accept the proton, and you form a hexa-aqua complex again. This is just the same as what we've had here. It is charged again, so you'll form another charge because we're now replacing, or well, we are losing the 3 OH- charge and replacing it with a neutral one, so it's just the charge of the chromium atom in the middle. So this is 3+, so it dissolves again. So you can see it acts as an acid or a base, and it changes depending on whether it's whether we're adding a base or whether we're adding an acid to it. Okay, so the reactions shown above are not ligand exchange reactions, okay? So this is why I was careful with what I was saying there. So these are an example of an acid-base reaction, okay? So the products are chemically changed, but it's done by the addition or removal of H+ ions. We're not actually swapping any of the ligands. We're not taking a ligand off and putting a new one on. All we're doing is we're swapping, we're either giving up a proton or receiving a proton, depending on what we're adding. So if we add excess ammonia, we've got to be careful with this. Obviously, these we're using hydroxides. So, for example, hydroxide for the alkali. But if we add excess ammonia to the solid chromium hydroxide, we actually do get a ligand exchange reaction, and we get a purple hexa ammonia complex here. So it's this solution is actually formed. So what happens is that all of these ligands that were attached onto the chromium are replaced completely by your ammonia ligand. So you do get something different. So it doesn't work with ammonia, but it will with a traditional, say, like sodium hydroxide. So here's the reaction here. So we get this green-grey solid, remember, that's being produced. And then if we add our 6 ammonia molecules here, then we form this complex here, which is purple, lovely purple colour. And obviously the ligands that were attached there are now separated. So we've got 3 OH- ions and 3 H2O. So that is a ligand exchange reaction. But this reaction over here is an acid-base reaction. So don't get them confused. Try and make sure that you can remember that. Okay. So let's have a look at how we make chromium complexes then. So most complexes can be made in a beaker. Okay, so it's pretty straightforward. However, some complexes, such as chromium 2 ethanoate, such as obviously this one here, this is the formula, they require a much more complicated method. So this is how we do it. So first of all, we add acidified sodium dichromate, which is orange, and that is reduced using zinc. So we've seen that reaction before, using zinc to reduce chromium compounds. So a green solution containing your Cr3 plus ions is formed. Then we get a blue solution containing your Cr2 plus ions. Remember, that's quite unstable, though, your Cr2 plus. So it needs to be in inert conditions. So you can see here, we've got 2 steps. So we've got your dichromate, which is orange, using zinc to form chromium 3 plus, which is green. And then your Cr3 plus is reduced further to Cr2 plus. So these are reactions which we've seen already. So remember, like I say, these are easily oxidized, and so they do revert back to chromium 3 plus quite readily. So this must be done in inert conditions. We cannot have oxygen around, because aerial oxidation can react or can send your chromium 3 plus back, chromium 2 plus back to chromium 3 plus. So normally we'd use a nitrogen atmosphere for this type of reaction. And so then secondly, then sodium ethanoate reacts with the Cr2 plus that we formed, and this forms a red precipitate of chromium 2 ethanoate, which is obviously our final product here. So you can see here, there's your Cr2 plus. This is your nice blue colour. It's a deep blue colour, and that forms this red precipitate. But it's mainly this step here. You can't just do this in a normal beaker, because the oxygen, unfortunately, does react with Cr2 plus to push it back to Cr3 plus, and we need that chromium 2 plus to form our final product. So that is the major difference there. So we do need an inert atmosphere, and that's quite difficult. You need some technical equipment to do that. Okay, so let's look at some transition metal substitution reactions. We've seen one of them already with ammonia reacting, obviously with your chromium hydroxide reaction there. Obviously you get ligand substitution. So a colour change, though, can exist when ligands in a complex exchange or substitute with each other. And these substitution reactions show ligands of a similar size being exchanged here. So let's have a look. So we've got a cobalt hexa aqua complex. We're reacting it with excess ammonia. And so what we get is cobalt or hexa ammonia complex here with cobalt and 6 waters. So here we've got a ligand exchange. We've kicked the waters off from here and replaced them with ammonia. Now, these is colour is pink, and it's octahedral. It's also octahedral on this side, but it's a straw colour, so the shape hasn't changed. So both the ammonia and water are similar size ligands, so they're the same size, and the same charges, so the complex shape still remains octahedral. But this proves that we do get colour changes when we're changing a ligand, and everything else remains the same, such as the shape. Here's another example. This is copper reacting with ammonia. Now this one's a bit strange, because we start with a blue octahedral shape, and we still end up with an octahedral which is dark blue. But the reason why copper is a bit strange is because we only get a partial reaction. Okay, so you can see here that the reaction occurs when the hexa aqua copper complex, try and say that one quick, reacts with excess ammonia. We don't get a full substitution. In other words, 2 of the water ligands have hung on, and the other 4 water ligands have been kicked off, and they're replaced with your 4 ammonia ligands there. So just watch out for that one, because it is a little bit strange. Okay, so This one we're going to do exactly the same, but these substitution reactions are going to show ligands of a different size being exchanged instead of the same size. So here we're going to use a slightly larger ligand, such as a chloride ligand, and a chloride ligand is larger than water or ammonia for that matter, and only 4 chloride ligands can fit around that. So we have a change in shape and coordination number as a result. So we're going from a 6 to a 4. So let's look at some examples here. So here we've got our cobalt hexaaqua complex again. We're reacting it with chloride ions. Could come from something like HCl, for example. And that's going to have a ligand substitution reaction. All these 6 waters are going to be kicked off, but we can only form 4 chlorines around it. Okay. So it's pink and octahedral to start with, and it goes to a lovely blue colour, and the shape is tetrahedral here because the ligand is much bigger. We can't fit as many of them round. And here's the copper one again. So copper, we react it with chlorine, that's fine. We get a full substitution here, and we get a blue colour, which is octahedral, and we get a yellow tetrahedral structure that's been formed. So this is showing a different size ligand being used, and the shape is changing here as well as the ligand. So here's another one, iron hexaaqua, add in the chlorine, and we form FeCl4. Again, we're going from a yellow, which is octahedral, and this is actually remains yellow, and it's tetrahedral. So we've got the same colour here. Okay, so you need to be aware of these reactions, and the colours obviously as well. Okay, so transition metal substitution reactions. So these different ligands, they can form different strength bonds to the metal ion. So this is where, for example, we're going to use Cn minus ions here. So so cyanide ligands, these actually form stronger bonds than H2O molecules, and this means that this reaction is not easily reversed, and so the new complex formed is much more stable, and actually we can see it here. So FeH2O6 cyanide and FeCN6 3-6H2O. Now, an interesting fact about this one actually in particular is this is actually added to salt, table salt. It's an anti-caking agent, so it stops your salt from sticking together. Now, if you look on the back, it'll say, so it'll have your cyano complex there. If you look at the back of the packet of salt, now it's just as well that this cyanide bonds very well to iron, because you don't want to be ingesting cyanide because it is horrendously toxic. So yes, so they do use it in there, and thankfully, because the bond's very strong, it doesn't break off the iron when you eat it, and it just gets passed out as waste. So that's fine. So multidentate ligands, these form complexes that are more stable than monodentate ligands. So let's have a look here. So you can see here we've got a multidentate ligand here. So we've got a monodentate ligand, which is water, 6 waters, and we're substituting it for this bigger ligand, this diamine molecule here. So we've got three of these. Remember, this is one of your bidentate ligands that you need to know. We're bonding it here, and we're replacing 6 ligands for 3 here. Okay, so we've got 3 ligands around there, and obviously our 6 waters have been kicked off. So this is bidentate ligand. It's an action that's really hard to reverse. You're forming something which is actually quite stable. So this leads us very nicely, you might have seen this one coming, to entropy. And entropy increasing forms a more stable complex. So let's have a look. So in a ligand exchange reaction, bonds are broken in the original complex and new ones are formed to make the new complex. So quite often the energy needed to break the bonds is similar as the energy released when new ones are formed, and so the enthalpy change, or the delta H, is small, and doesn't really play much of a role here, but entropy does. It plays a massive role. So you can see here we've got copper hexaaqua complex here reacting with our diamine ligand here. So we've got 3 of them, and you can see that we're forming our complex and 6 waters that's being produced. Now, what's key here is that we're breaking 6 coordinate bonds on the left here, and we're forming 6 coordinate bonds there, so the energy difference is going to be pretty small. So this is not considered a reversible reaction, as the complex that we formed is actually more stable than the complex that we started with, which is our hexaaqua complex. This is despite the fact that the enthalpy change is relatively small. There's no real incentive to form it, so it is actually really stable. Now, this actually plays into the kind of entropy side of it, which we'll look at now. So the increase in stability is known as what we call the chelate effect. So when we substitute these monodentate ligands with bidentate and multidentate ligands where they can bond more than once, we create a solution with more particles in it. And we have what we call an increase in entropy. So remember this. So reactions that have an increase in entropy are much more likely to happen. So if you're not sure, go and have a look at the video that I've done on entropy changes. So that would be, so that just makes sure that you're looking at, that you understand how entropy works. But if you look at this reaction, so if we look at EDTA4, for example, 4 minus as an example, this is a multidentate ligand, so it can bond numerous times, 6 times in fact, and you'll see that the number of particles increases, so the entropy increases. This is really difficult to reverse, because if you did reverse it, it means you're going across to an unfavorable entropic system. You're going from something with loads of particles and a disordered arrangement to something that's ordered. So here we are. So you can see here we have your hexa aqua EDTA. There's your complex that's formed and 6 waters. And so effectively you have 2 particles going to 7. That is entropically favourable. So going backwards from 7 to 2 isn't going to happen really, unless you put in a lot of energy to go against that. So this is why EDTA or EDTA based complexes are actually really stable. Okay, so the colour of complex ions depends on the size of delta E, which is affected by the change of oxidation state, coordination number, and the change in ligands. Remember, we looked at the delta E part about colour. So here's an example of a ligand substitution where the coordination number is the same and so is the shape. So you can see here that we've got hexa aqua complex. The shape is remaining the same, but like I say, we're going from pink to a straw coloured. So this is where we're actually, the coordination number is staying the same, and the shape is remaining the same, but we're changing the ligand. So the ligand does have an impact on colour. And here's an example of ligand substitution where the coordination number changes and so does the shape. So this is normally when we're replacing a smaller ligand for a bigger ligand. So a classic example, here's one here, so replacing 4 water ligands with 4 chloride ligands. So we're changing the shape, and so therefore the colour will change. So we're going from pale blue octahedral to a yellow tetrahedral structure because we're changing the shape here. So all of these changes here have an impact on the size of that delta E. That's the gap between the d orbitals that are split. Okay, so let's look at some examples where the oxidation state changes, but the ligands and coordination numbers remain the same. So here you've got Fe2+ going to Fe3+. So pale green, still octahedral, but yellow and octahedral. So all we're doing is changing the oxidation state. And here's your vanadium one, going from vanadium 2+ to vanadium 3+. So it's violet, octahedral, and green, but still octahedral. So this is a really important difference. It's not just the type of ligands or the shape, it's also the oxidation state, which also has quite an important role with this as well. Okay, so what we're going to do is we're going to look at the colours and summarise this really, because we've seen a lot of different reactions here. So we're going to look at the ions that we need to know, we're going to look at the colours they are in solution, and what happens to them when we add a little bit of hydroxide and ammonia, which is this bit here. Okay, when we add excess hydroxide to the precipitate that we form, and then when we add excess ammonia to that precipitate. So basically this is just going to summarize the full lot. So copper, excuse me, so copper when dissolved in water is a blue solution. Iron when dissolved in water is pale green, so it forms that iron 2+, forms a pale green. Iron 3+ is yellow, and cobalt is a pale pink colour, so it's a nice colour. Okay, see if you can do this. Obviously, we've gone some of these reactions already, so see if you can work this out. So when we add a small amount of hydroxide or ammonia to the aqueous solution, see what we form when we add it to Cu2+. Have a think. Okay, that is a copper blue precipitate. It will be a precipitate because we formed a solid compound, so we get CuOH2 and H2O4. So see if you could do the next one. Okay, so this one is FeOH2, H2O4, and is a dirty green precipitate. Okay, what about Fe3+? Have a go at that one. Okay, so this one is FeOH3, H2O3, again, they're all solids because we're adding a small amount, so we're forming a solid complex, remember, that's neutral. So if it's neutral, it doesn't have a charge, it forms a solid precipitate. So this is orange, an orange precipitate. And then what about cobalt-2+? Okay, so this one is a blue precipitate. Again, the same reason. So notice how many, notice the shape of these, how many, say, OH minus ions are actually on here. So with a Cu2+, we've got two OH2s. With Fe3+, we've actually got 3 of them, as you can see, because we need 3 of them because we've got a 3+ charge. Okay, so what happens if we take this blue precipitate here and we add, for the copper one, and we add an excess hydroxide to the precipitate? What do we get? So have a think. Okay, well, this one is insoluble in excess sodium hydroxide, so actually we don't get any change at all. Okay, and what about the next one for Fe2+? Okay, so this one is also insoluble in excess sodium hydroxide, there's no change. And for Fe3+, it's also insoluble in excess sodium hydroxide, so there's no change there. And finally, for cobalt-2+, it's insoluble, so dead easy. Okay, so you don't need to worry about that. Okay, so what about the ammonia one then? So when we add excess ammonia to that precipitate, what do we get for copper-2+? Well, this is the funny one. This is where you get part ligand substitution and you actually get a dark blue solution. So remember, some of the ligands, some of the water ligands remain, and 4 of the ammonias actually substitute some of the hydroxide and water ligands. So what about Fe2+? Well, this one's insoluble in excess ammonia, so there's no change. What about Fe3+? That one's insoluble as well. And finally, cobalt-2+. This one forms this browny yellow solution. Okay, so it turns brown after a while if you leave it a bit, and so does this one as well. This one at the bottom, this turns brown if it's left for a while. So you need to know these reactions. You need to know the colours, and you need to know what's happening. So this is just summarising some of the reactions that we've seen. Okay. So let's have a look at the complex ion solution equations this time. So the same reactions that we've seen before, we're going to apply some equations to it. So this is just for your reference, really. So you do need to know these reactions, but you can work them out effectively. So your copper one, remember, you're adding 2 amounts of, this is when a small amount of hydroxide ammonia is added. Because it's a 2+, we only need 2 of these, and that will form these complexes here. So we get these type of complexes, and obviously the water and ammonia. It's exactly the same. Oh, sorry, no, it's not. We're going this way. Sorry, I don't even know what's how I've set this up. So your copper 2+, when we add an excess hydroxide to the precipitate, and then when we add excess ammonia. So when we add excess hydroxide, remember there's no change. We've seen that from the previous one. But with copper, we get this partial substitution of ammonia. So we go from our precipitate here, and we get a partial substitution. But we've seen that before. Okay, so for iron, it's exactly the same for iron regarding the 2 hydroxides and 2 ammonias. And nice and easy, it's insoluble in excess and hydroxide and ammonia, so there's no change. Now Fe3+ is a little bit different because we need 3 of them to form our neutral solid substance. So it's 3 OH and 3 NH3. And we get insoluble for both of them at the end there. And finally cobalt, again, same type of reactions. But it's insoluble in sodium hydroxide, all of them are. But when we react it with ammonia, excess ammonia, then we form this complete substitution of the ligands, and we get this hexa ammonia cobalt complex there. Okay, so we're just moving on to the final part of the video. There's a few slides on this, but it's the final section. We're just looking at catalysts. So catalysts can be homogeneous or they can be heterogeneous. So heterogeneous, this is a catalyst that is in a different phase from the reactants. Okay, so hence the word hetero. The catalyst is in a different state to the reactants. For example, the Haber process. So the Haber process is the manufacture of ammonia, which is used as a fertilizer in farming, in agriculture. So a solid ion catalyst is used, and this is clearly in a different state to the gaseous states that we've got there. So if we increase the surface area of the heterogeneous catalyst, if we increase the surface area of that, then the rate of reaction will increase as well. So this means that more particles can actually interact with the catalyst at the same time. So that's quite a good thing. Whereas if we look at a homogeneous catalyst, these are catalysts that are actually in the same phase as the reactants. So generally, homogeneous catalysts are in aqueous reactions. So for example, sulfuric acid is used as a catalyst to help to make an ester from an alcohol and a carboxylic acid. And so homogeneous catalysts form an intermediate species by reactants combining with the catalyst, which react to form products, and the catalyst is reformed again. All catalysts are reformed. That's quite important. Okay, so as transition metals actually have variable oxidation states, as we've seen already, they are actually good catalysts by receiving and losing some electrons in the d orbitals to speed up reactions. So they play a vital part. So, for example, the contact process uses vanadium to make sulfuric acid, which is a vitally important bulk chemical used in chemistry. So, in the manufacture of sulfuric acid, we use V2O5, so that's vanadium 5 as the catalyst, and it's used to catalyze SO2 to SO3, and this is a heterogeneous catalyst because it's in a different phase or different state to the actual reactants. So you can see here first the reaction happens is first the V2O5 oxidizes sulfur dioxide to sulfur trioxide, and itself is reduced to V2O4. So the reaction that we need to know is V2O5, this is the heterogeneous catalyst, V2O5 reacts with sulfur dioxide to form V2O4 and sulfur trioxide, okay? And then that second reaction that happens here is the vanadium, the V2O4 that we've produced there, is oxidized by oxygen, and that reforms back your V2O5, okay? So that's very important. So catalyst must always be regenerated. So catalysts are used to make these products much quicker, or you can lower the temperature. So that's better for the environment because we're not burning fossil fuels to make this product. And also it saves on time and it saves on money as well, because if you're producing this product quicker, it means you can get it out to your customers much quicker, but also the energy needed to make that product is being reduced. So therefore, clearly that's going to save money, a little bit of money as well. So heterogeneous catalysts can be poisoned by impurities. So we've got to be careful with this, with heterogeneous catalysts. So impurities can bind to the surface of a catalyst, and this blocks the active sites for reactants to absorb. So just like with the contact process where we produced sulfur trioxide, that sulfur trioxide you then react with water to form sulfuric acid. So that was the last step there. So we're using that catalyst to produce sulfur trioxide. But that site that's reliant upon the vanadium to actually react, for substances to adhere to the surface of the catalyst. The catalyst is littered with impurities, then there's no space for them to react. So when an impurity blocks that site, we call it poisoning. Okay, so we call it catalytic poisoning. So catalytic poisoning reduces the surface area for reactions to happen, and this slows down the reaction. So that's not a good thing at all. So the Haber process, let's go back to this reaction where we've got nitrogen reacting with hydrogen to form your ammonia. So the hydrogen is made from methane, and methane contains sulfur impurities. So here here's our catalytic poison as an example. So any sulfur that is not removed will adsorb to the surface. Notice the word D, adsorb. Surface forming iron sulfide. And so this catalyst is less efficient. So you can see here's our iron sulfide here. This is the nitrogen and hydrogen. These are the reactions I want adhering to the catalyst surface. But now we've got this, which is stuck to the surface, and we can't do any reactions now on this bit of the catalyst because we've got an impurity there. So this is what we mean when we say we've got catalytic poisoning. So a poison catalyst means that we get less product is made, and the catalyst needs to be replaced and cleaned more often. That's time, and that costs money. And obviously there's an increased cost of the chemical process because the catalyst isn't working as it should be. So it's not reducing the energy required or lowering the activation energy, for example. So that's not a good thing at all. Okay, so substances adsorb to the surface of a solid heterogeneous catalyst. So we've seen that before. So reactions occur on solid heterogeneous catalysts. So they occur on the surface. they bond to that surface, and we call that adsorption, as we've seen. So with a D. So that's not a mistake. That's deliberate. So it's with a D. So because they add to the surface. So the bonds in the reactants weaken and break to form radicals. So these are atoms or molecules with an unpaired electron, if you can remember from year 1. And these radicals then react with each other, and these make the new substances that we need. So the new molecules are then released from the surface of the catalyst in a process called desorption. So this is where the bonds between the atoms and the catalyst surface then start to break away. And so in this reaction, what we're doing is we're showing the formation of ammonia using an ion catalyst in the Haber process that we've seen already. So here we go. So here's our ion catalyst surface. And so our nitrogen and hydrogen. So these bond to the surface, and this is called adsorption. That's what the yellow dots represent. And then what happens is they break away. Once they react, they form the radicals and react to form our products, which is ammonia, and that's desorption. So they break away from the surface. This leaves the surface then free to undergo another reaction for more molecules later on. So it's pretty straightforward. So why do we use catalysts then? Well, like we say, they're good because they lower the temperature for the reaction to actually happen. So this means less money is used for the fuel, and so less CO2 is produced, because normally the fuel we use is a fossil fuel, so something like that. And it speeds up the reaction as well, because it provides an alternative pathway for that reaction to proceed by. So there are environmental benefits as well as economic benefits, and lower temperatures and pressures means less carbon dioxide is produced, which we know is a greenhouse gas, and also because we're using a catalyst, less waste is produced because they allow the catalysts allow scientists to develop routes with better atom economies. So, for example, instead of producing it via a 5-step mechanism, we could do it via a 2-step, which means we get less waste products at each of them steps. And so catalytic converters are used quite often in cars, and these reduce the levels of pollution. So they're made from a rhodium, platinum, and palladium alloys. So these are some of the most expensive elements in the world. They're really expensive. And its job is to convert carbon monoxide and nitrogen monoxide, so some of these toxic gases, into less harmful gases, such as carbon dioxide and nitrogen gas. And if you look on the underside of a car, a catalytic converter is actually the bit, it's the box bit that sits underneath the car, and you can see it there. So inside this box, you've got a mesh that's peppered with rhodium, platinum, and palladium powder. That's then obviously the gases then pass through that when you turn on the engine. Okay, so catalytic converters can also be poisoned in cars. Obviously, if they can be poisoned in reactions such as making ammonia, they can also be in a car as well. So, for example, lead poisons platinum catalyst and catalytic converter, and lead was found in petrol. However, it's no longer used. It used to be called 4-star or premium unleaded. It used to be called, but it used to be, and then it used to poison these catalysts, which caused all sorts of problems and made over time all the cars weren't as efficient as what they are today. But this is why we have the word unleaded. So you see the word unleaded because there was options years ago where you had leaded petrol and you had unleaded petrol. So you had a choice, and now we don't have leaded petrol at all, because clearly you can see the reasons why. Obviously, this reduced the effectiveness of the catalyst with the lead in the petrol. And so the poison adsorbs to the surface of that catalyst, and then obviously that blocks the effectiveness of the catalyst completely. Okay, so here we can see the poison or the lead taking up the space of some of the surface of a heterogeneous catalyst. So you can see here. So there we go, and these just bounce off the lead catalyst. So also the lead impurity on there, as you can see, it's taken up the space. So that's not that wasn't good. And clearly, if you had to replace a catalytic converter, they're not cheap, because platinum's a very expensive metal. So you don't really replacing that all the time. So they weren't particularly good. So new formulations of fuel help to produce and improve efficiency and reduce pollution. Okay, so let's look at homogeneous catalysts. So homogeneous catalysts, they have a unique energy profile. So remember, homogeneous means they're in the same state. The catalyst is in the same state as the reactants and products. So they have two activation energies. Now, you would have seen this in year one, these energy diagrams. But let's say we've got reactants and products, and we're showing our reaction progress here. So normally, with this type of reaction, this is an activation energy with no catalyst at all. But when we add a homogeneous catalyst in, we know a catalyst reduces the activation energy. So this is the activation energy with the catalyst in the first step. So you can see the catalyst lowers the activation energy. So we have this kind of double step here. We have a first energy profile here, and then it drops. And then we have another bit of energy it required to then finally produce our product. And the reason why, here's the second step, okay? The reason why is because intermediates are formed at this point. So a catalyst actually produces an intermediate, then we need a little bit more energy to produce our final product. So there we are. So homogeneous catalysts, they form this intermediate species, okay? And the catalyst is obviously reformed again. So this is why we have this unique double bump in our energy profiles with using a homogeneous catalyst. So homogeneous catalysts, they combine with reactants to form intermediate species, which then react to form products, and then obviously the catalyst is reformed. And this will fit in with the energy profile that we've just seen before. So a catalyst lowers the activation energy required for the reaction to occur. So it's really, really important. The catalyst is always reformed. It's never used up. That is the purpose of a catalyst. So, for example, here's an example of where we use a homogeneous catalyst. So the oxidation of iodide ions using peroxide disulfate as a catalyst. So this is S2O8 2-. So the reaction uncatalyzed is very slow. So it's not a great reaction to use if you want something quickly. So we are trying to react negatively charged ions, which normally would repel each other. We're trying to react these together. And so as a consequence, the energy profile is really high. So you can see here, we're trying to react this, which is 2-, reacting it with another minus ion, it's just not going to happen. I mean, that's really difficult. You're trying to react these two together, that isn't going to happen. So this is where we need almost like an intermediary between the two. So we have, if we use Fe2+ as a catalyst, what we can do is lower the activation energy, so the energy required to react these two ions together, and speed up the reaction. So the first part actually involves the reduction of the peroxide disulfate first. So here's your peroxide disulfate reacting with the ion catalyst. This produces Fe3+, and obviously your sulfate ion, which is obviously at the end here. So you can see here the Fe2+ is oxidized to Fe3+. Your peroxide disulfate is reduced to sulfate ion. So that's the first step. The second step is that Fe3+ intermediate that's produced in the first part reacts with the I-, which is also floating around. So this is the second part of this reaction, to form Fe2+. So you've reformed your catalyst back again, and then you form iodine. So it's quite clever. You can see how that ion is actually getting involved with the reaction, but it's forming an intermediate, and then you've got this two-step process. Hence why you get that double bump in the energy profile diagram that we'd seen just before. Okay, so we can test for iodine. We know if iodine is being produced because if we add starch to it, it turns that blacky blue color if iodine is present. You would have seen that in the peroxide disulfate titrations where you add iodine to make sure you can see you add starch to test for the iodine. Okay, so the last bit is autocatalysis. So autocatalysis, as the name suggests, is basically where the reaction catalyzes itself. Okay, so autocatalysis is another form of homogeneous catalysis, and it's where the product catalyzes the reaction. So it's a very smart way of imagine if all reactions could be done via this way. But an example of autocatalysis is where Mn2+ is the catalyst in a reaction between C2O4 2- and MnO4-. So again, remember the catalyst is always reformed, it's never used up. So Mn2+ is a product and a catalyst. Okay, this is why we call it autocatalysis. And so this means as the reaction proceeds, as it goes along, the amount of product increases, and so does the rate of reaction. So it actually starts to run away with itself. So the reaction uncatalyzed is really slow because we're trying to react two negatively charged ions together, and these would repel. So it doesn't, obviously it requires loads of energy to do that without a catalyst. So you can see here, there's our MnO4 minus ion here and our C2O4 2 minus. These two would never react together normally, so we need a catalyst to help that go. So the first step, the Mn2 plus, catalyzes the reaction. So this is this product here. Mn2 plus catalyzes the reaction, converting MnO4 minus into Mn3 plus. So that's the first step that happens there. So we form this Mn3 plus. Okay, so we'll have some Mn2 plus in there already. And then secondly, the Mn3 plus formed reacts with the C2O4 2 minus, and Mn2 plus ions are reformed back again. So it's very important that this is the product, there it is there, but it's also the catalyst, but it's reformed. That's very important. And that's it. So it's a very, very big topic. So that is everything you need to know about transition metals for EDEXCEL for topic 15. There is a full range of videos for EDEXCEL on Allery Chemistry YouTube channel. They're all there for free, as well as some whiteboard lessons as well, looking at specific topics, and as well as some exam work-throughs as well. So there's plenty on there, very comprehensive and targeted. If you study EDEXCEL, this is ideal for you. So all I ask is that you just hit the subscribe button. That would be brilliant, because you don't charge anything, so that would be perfect. Also, if you do wish to purchase these for your own use and use them to print them off and use them at your own leisure, click on the link in the description box and you'll be able to get a hold of them there. Phew, that was a lot. Right, okay, that's it. Bye bye.